The power connections of the battery are used for transferring the power between the battery pack and the vehicle systems as well as the charging units. The BMS is in charge of controlling the transfer of power, and in this section we will study the role and the features that the BMS has for controlling the power connection. In a battery, the power path is the electrical circuit that will connect our battery to the vehicle systems and the internal charger. That is here highlighted with the red line. Across the power path, we can find different components. For instance, we can find or we can distinguish the current sensors that measures the flow of current through this power path. We have the battery. We also have fuses that will protect the systems by disconnecting the power path during overcurrent events. And we also have the contactors that are one of the most critical components in the power path. These contactors are like high current switches that manage the connection and the disconnections of the battery pack. The two main types of contactors that we have are the relays or the electromechanical switches that have they have very high current handling capacity, and these are durable and they are capable of operating like with high currents, but they are also very slow, and they are subject to wear over time due to the mechanical parts that are moving inside of these relays. On the other side, we also have FETs, and the FETs are solid state switching devices. They have a greater reliability, and they can be used, for instance, several of these devices in parallel to handle high currents. However, they require a very precise design in order to avoid that all of these elements that are in parallel are having the same current, and also they are a little bit more pricey, but it is one of the technologies that are currently being introduced into the BMS because of the development of this solid state technology that right now allow us to have also switching capabilities at very high voltage levels that some years ago was not possible. The configuration of the battery management system power paths will determine how the energy is being transferred from the battery to the loads and how this energy is going to be routed alongside the circuit. The power path configurations are primarily categorized based on the contactors and where these contactors are placed. For instance, we can have contactors in the low side, it means in the negative terminal of the battery, or on the ground, or in the high side, it means in the positive terminal of the battery. This is one of the classifications that we can have of the power path, but also we can distinguish between either we are having single path for charging or discharging, as this example, or if we have separate paths for charging and discharging, as this other example over here. We will look then now and review the advantages, disadvantages, and when each of these systems are being used. So let's start with the low side and single path configuration. This is a straightforward design in which we have two contactors that are placed in series, and both of the contactors are in the ground side of the battery. As you can see, as both contactors are in series, it means that we have a single path that is being used for charging and for discharging. The charging and the discharging FETs, in this case, will be sharing the same connector that is here, and also they will be sharing, there will be the same current flowing through each of these contactors. In this case, they are FETs. It means that both FETs are designed to be and they are rated to handle the maximum current of our system, that usually is the current that we deliver during discharge. And and this increases the size of both of these systems, of these contactors, and also the heat generations that they are that they have. As both of those FETs are close to the ground and they are connected in the ground path, this setup eliminates the need for advanced high side control circuitry. Usually when we have switching devices in the high side of the battery, as these contactors will be floating, we need to manage them with very costly and very specific control circuits, and in this case that is not needed. This allows us to have a simple implementation and also a cheaper implementation, and that makes this implementation very popular for applications that are budget sensitive, for instance in electric vehicles or in energy storage systems that are like in a smaller scale energy storage systems. This simplicity comes with a critical drawback. That is, as you can see here, when the BMS activates any protections and when any of these two contactors are open, at the end we are going to lose the connection to the ground. So if I have any system directly connected here, the ground of this system, they have to be insulated, because if they need to share the same ground, they are going to be misfunctioning, and it is not going to be ideal for any of both systems. Also, this comes with the challenge in the case of communications that relied on stable ground connections. If we have isolated communications or if we have isolated systems, this wouldn't be a problem. In high voltage systems, usually we have completely isolated components, and in that case we can even put contactors in the low side and in the high side. Then we have the high side path configuration, and in this case both of our contactors are in the positive side of our battery circuit. The high side single path configuration is something that is widely used. As you can see here, both contactors are also in series. It means that there is only one path for charging and discharging. These setups ensure there is a better management of the power path, because we ensure that the ground is always connected to our systems, and because of that we minimize the risk of accidental faults because of losing that reference. It also has a clear and effective separation of the battery from the systems during there is any fault condition and when any of these contactors are open. However, as was explained before, they require robust high side drivers. These are floating drivers in case that we are using FETs. When we are using relays, for instance, it is not such a critical disadvantage. And in addition, we can have separate paths. In this case, we have a configuration that has two FETs in the high side, and they have this separate configuration. As you can see here, we are having independent connectors, and contactors. We have one contactor and one connector for charging and another one for discharging. This is also possible to be implemented in the low side, so connected both contactors connected to the ground. In this parallel configuration, as we are having separate contactors and as the current of charging is gonna go through a different path than the current from discharging, this allows that each of these These FETs can be sized accordingly to their specific current rating and to the current rating of its function. And this is important because, for instance, during charging and the charging currents are usually much lower than the discharging currents, and this results in reduced losses and in a more efficient system. On top of that, some of other advantages. So we mentioned already that this configuration optimizes the FET sizing and has less energy losses because we are optimizing the current in each of the paths. But also another advantage is that as we have two paths, the unused connector remains electrically floating, and when it is not in use, it will not reflect any voltage. So for instance, if we are not charging, we can completely disconnect the charge path, and in that way there are not going to be any voltage reflect here, and this reduces the risk of accidents and also reduce the risk of electric shock, for instance. This configuration is ideal in electric vehicles or in grid storage systems. However, it is more complex, and as you can see, it also have some additional components, both for the, for instance, for the additional connectors that we have to use here. So it can have a higher cost. There is another path that we have to include in our power connections, that is the pre-charge path. And it is necessary because when we connect our battery to capacitive loads, for instance with the DC link capacitor that are in the inverters and that are a common feature in high voltage systems, in those cases we need to protect our circuit. These capacitors, when they are first connected to the battery, they draw a very large amount of currents. There is a peak of currents that is generated, and you can see over here, this is an example of the current when it is not limited. And the BMS must be capable of managing these high currents and limit that current. Without the management of that, this can lead to several issues. For instance, we can damage components like the contactors, the connectors, the cable. We can blow fuses of our system, leading to costly repairs. And we can also, for instance, generate excessive heat, and the degradation of the system and the components of the over time will cause a final failure because of that. To handle this, the BMS employs the pre-charge circuit. That is the circuit that we are seeing here, and this circuit has the role of limiting the current flow of the capacitors and to gradually increase the voltage of the capacitor to avoid that peak current, and we will explain that in detail in the next slide. So as mentioned, the pre-charge path is specifically designed to limit the inrush current and to protect the components during that initial connection phase. It consists of two main elements. First, we have the pre-charge resistors, and then we have also a pre-charge contactor. Both of these are connected in parallel to the main contactor of the battery, that at the end will be in series between the battery and our load, and also our capacitive load. This is an explanation of the sequence and how this system will work. So in the first steps, when we connect the battery and the battery is charged and we connect it to our load that includes a capacitor, and that capacitor is not charged, our system will deviate the current through this pre-charge resistor over here, and this resistor will limit the current flow to a safe level, and this will prevent the sudden current peak that we depict in the previous slide. As the capacitor begins to charge, the voltage of the capacitor will rise and the current flow will decrease little by little. The BMS will be continuously monitoring that voltage across the capacitor, and it will ensure that that voltage reaches a voltage that is very close to the battery voltage. At that point, we will then connect the positive path, and then after that we will be able to disconnect the charge. I skipped one slide here and I came to this one that exemplify better what I was explaining, and this is the sequence and the process of the pre-charge connection. I will repeat it here just to be sure that we are in the same understanding. So when we want to connect the battery for the first time, the first step that we have to do is to connect the negative contactor of the battery. In this case, as you can see, our battery has an our BMS in handling a contactor in the ground, in the negative terminal of the battery, and then it is also handling a contactor in the positive terminal of the battery plus the pre-charge contactor. Those are the three ones that we will be using to control the flow of energy. So the first step is then connecting this negative contactor, establishing a path from the battery to the load by means of the ground, and this will prepare our circuit, and it will prepare our circuit for performing the pre-charge phase, while it is still keeping insulated the high voltage positive path, since both of these contactors are open. Then in the next stage, in this case, we activate the flow of currents through the pre-charge resistor, that is this one over here. The current will be flowing in this direction that I'm highlighting, from the battery to the pre-charge contactor, the pre-charge resistance, and finally to our capacitive load. This resistor will limit the current, and as well mentioned, it will allow the capacitor to charge gradually. Here we will be then monitoring the voltage, and to be sure that that voltage will be increasing until the point that the voltage in the battery pack equalize the voltage in the load, or in this capacitive load. Once the capacitor voltage is very close to our battery or our system voltage, in that case, in that moment, we close the main positive contactor, and once we do that, we are gonna bypass the charge resistant currents, and we enable the full current flow that is needed on our system for operating. So in this case, after I activate this contactor, all the current of the system will go through it. And finally, we will disconnect then the pre-charge, as you can see here, and with the main contactor already engaged on, the pre-charge contactor is isolated, and we isolate these pre-charge resistors to avoid any power dissipations during the normal operation of the battery. If during this process we have any failure, and maybe there is failures during charging the capacitor, or maybe we have any failure in these intermediate stages, in that case the system voltage will go back to a protective state when all of these contactors are open, and the system insulates the battery and protects all the components from potential damages.